Okay, so today we have Jeremy Hahn, who will be telling us about connections between the thsegal and Lichtenbaum-Quillen conjectures. Thanks.
All right. So the first thing I want to say is that any work of my own that I'm going to talk about here, and I don't know whether I'll get to it or not, that's all joint with Dylan Wilson. And the second thing I want to say is thank you, of course, very much for inviting me. It's a huge honor, and I see a big crowd here, so I hope this comes out okay. And I'm going to talk about the Lichtenbaum-Quillen conjecture, or the Quillen-Lichtenbaum conjecture. People seem to go back and forth on how to name that. And if you don't know too much about this, it won't really be necessary. Basically, I'm going to say some things about K-theory. I'm going to say some things in equivariant homotopy theory, and maybe you know those things. And at the end, I'm just going to present a whole bunch of calculations, which are hopefully understandable and interesting, even if you don't know what I'm saying earlier in the talk. So I'm just trying to remind you here about the Quillen-Lichtenbaum conjecture and what it says. So it says that if you have a suitably nice classical ring, and by suitably nice, we mean probably something like a regular ring, so there's some kind of smoothness assumption, and we probably want some kind of finiteness assumptions. In that situation, there's supposed to be this very interesting fact that the mod p algebraic K-theory of the ring is isomorphic to that mod p homology when you invert the bot element, but it's only an isomorphism in large degrees. It's not an isomorphism in all degrees, which means there must be something subtle going on. And this can be proved for by trace methods, by TC and TR and things like that, at least in the p-adic setting. So Hesselholt and Madsen accomplished this spectacularly when they proved this conjecture for things like the ring of p-adic integers. And the sort of most modern recent theorems along these lines for p-adic rings are well written up by Akil Matthew. All these kinds of trace methods proofs have really been streamlined using modern technology by people like Nikolaus Schulze and Anton Nicolas' TR work and Akil Matthew's work using that stuff. So that's sort of the point of view I'm going to eventually get to, is using trace methods to try to prove isomorphisms between mod p algebraic K-theory and its localization. But let me just say that if you don't want to just know this for p-adic rings, but if you want to know the Lichtenbaum-Quillen conjecture for something like the p-local integers, that is now known, but the proof involves heavily the very deep work of Voevodsky and Rost, and in particular the full strength of the Bloch-Kato conjecture. So I like to think that what the motivic homotopy theory accomplishes is the ability to go from some kind of p-adic ring and know something about a p-adic ring to know something about a p-local ring. And mainly I'm interested in this from the point of view of a chromatic homotopy theorist. There's an amazing theorem by Asuni and Rognus from 2002, which gives a kind of generalization of this Quillen-Lichtenbaum conjecture, where we no longer insist that the ring of input be classical. So what they did was, when p was larger than or equal to 5, they studied L, also known as BP1. So this is the p-local atom summand. The summand of connective complex K-theory that localized at some prime p. And they calculated something about the algebraic K-theory of the p completion of this L. Again, the p completion is present because the techniques are trace methods. And they calculated this mod p v1 and observed that if you map into the same thing with v2 inverted, then this is a pi star iso, again, for star sufficiently large. So it's clear that this is some higher chromatic version of the previous statement, which is very intriguing and led to a lot of conjectures that were well explained by Rognus in various talks. And I'll just remark that using, again, this kind of blockato work, Brost and Vygotsky, you can deduce a similar statement for L itself. So a similar fact for the algebraic K-theory of L mod P in V1. And again, that's the difference between some P local setting and some P complete setting. So the question that I want to approach in this talk, or attempt to explain in this talk, is why is this only true for star greater than 0? What is happening? What's the input to this kind of thing that allows you to conclude something only for sufficiently large degrees and have something fail in small degrees? So there's a well-known answer to that question in the situation of classical rings coming from Voevodsky's work. But in the situation of ring spectra, it's maybe a little bit less clear what's happening in low degrees. And I want to propose sort of a philosophy, which I think goes back some time, that the thsegal conjecture is responsible for some of this, for some of these things only happening in large degrees. So let me just tell you a little bit about the thsegal conjecture. And in particular, let's start with this sort of classical thsegal conjecture that you learn about if you learn equivariant homotopy theory. So the starting point is always supposed to be this theorem of Lin, which says that this RP minus infinity infinity, which is the homotopy, sorry? No. The RP minus infinity infinity, which is the homotopy limit of some Thom spectra over RP infinity, that's somehow just the sphere or the desuspension of the sphere after a 2 completion. So that's the original formulation of Lin's theorem. But from a modern point of view, we tend to think about this in terms of the C2 equivariant sphere spectrum. And in particular, what this Lin's theorem says is that the map from the fixed points to the homotopy fixed points is an equivalence after 2 completion. So the proof of that involves this fundamental pullback square that some of you may have seen before, relating all of the various kinds of fixed points in C2 equivariant homotopy theory, the geometric, the Tate, and the homotopy fixed points, as well as the genuine fixed points. So essentially, for formal reasons, these geometric fixed points are just the sphere, while the Tate fixed points are the suspension of RP infinity minus infinity. And therefore, this top map being an equivalence, this map being an equivalence after 2 completion is the same question as asking for this map to be an equivalence after 2 completion, and that's Lin's theorem. So this has been generalized in many directions. So just to name one of them, there's a generalization where you, first of all, we're going to work with a group that's cyclic of some prime order, but not necessarily C2. And then we're going to generalize the sphere and think instead of the sphere about the norm of any spectrum. So we look at the Hill-Hopkins-Ravenel norm of some spectrum, which is essentially the p-fold tensor power of the spectrum permuted by the cyclic CP action. And there's a sort of amazing theorem about that norm, which generalizes the classical Lin's theorem. And I think this was first really discovered by Luna-Nissen and Rognus, but then proved in its most general form by Nicholas and Schulze in recent work. And so they showed that at least for a bounded below spectrum, one always has this property that the genuine fixed points are equal to the homotopy fixed points after some kind of completion, after a p completion. So after a p completion, norms of bounded below spectra are Borel. Their genuine fixed points are the same as their homotopy fixed points. And equivalently, by that same pullback square, we could say that the map from the geometric fixed points to the Tate fixed points is in equivalence after P completion. So this, for formal reasons, again, is just the original bounded below spectrum one starts with, and this is often written as X tensor P TCP, because again, that norm is just the p-fold tensor power of X permuted by the cyclic action. So in other words, sort of the ultimate version of the classical thsegal conjecture, at least for the cyclic group of order P, is that this map from X to X tensor P Tate CP that appears at the bottom of the standard pullback square for the norm of X, this map is an equivalence after P completion. And it goes by a name, it's known as the Tate diagonal. Just to repeat that one more time, it is an equivalence after P completion, or since we're in some bounded below setting, it's an equivalence mod P. And maybe I should remark that there are many generalizations of this thsegal conjecture. I mean, we've already generalized Lin's theorem. So one of the classical generalizations is to think about larger groups. So there are variations of the thsegal conjecture for larger groups than CP. That's not the kind of direction I'm going to be talking about for other groups. But presumably, there are many generalizations of the thsegal conjecture. I think Hahn sometimes calls this the thsegal program, and we should be aware that there's probably going to be more and more generalizations as the years go on. And the other thing I wanted to mention is that modern proofs of the thsegal conjecture or of Lin's theorem, they often are nowadays deducing this kind of thing from stronger statements. So modern proofs of Lin's theorem often see it as a corollary of some perhaps not fully explored stronger statements in equivariant homotopy theory. It's a corollary of deeper results. And so, for example, I'll highlight this work of Carrick, and who concludes Lin's theorem as a corollary of a stronger result, which is the HHR slice theorem. The reduction from the slice theorem to Lin's theorem is very clever. And I guess there's also some work of me and Dylan deducing Lin's theorem from a computation of real Hochschild homology. So there's all sorts of ways nowadays of thinking of Lin's theorem as a special corollary of some stronger statement. Okay, but I want to talk about the THH thsegal conjecture, which I think was something really first highlighted again by Luno Nielsen and Rogness, so it had appeared in several forms earlier. So to give you the THH thsegal conjecture, I have to define THH, and hopefully that's the last bit of theory I will throw at you, and then we'll make some calculations and some examples, which you can understand even if you don't understand all the objects involved. So the standard definition of THH for an E1 ring is by this tensor product, R tensor over R tensor R op R. So that's some funny formula, but a magical fact about that formula is that the resulting object has a circle action, and it not only has a circle action, but it has an additional piece of structure, which is nowadays known as the cyclotomic Frobenius. So it's some map phi from THH of R to THH of R TCP, where the CP action is coming from the fact that CP sits inside the circle, which acts. So I'll just remark that there are many ways of constructing this map phi, and maybe the most useful or elegant one nowadays is by Nicolas and Schulze, and they really construct this phi using functoriality properties of the Tate diagonal. So really the cyclotomic Frobenius is highly related to this Tate diagonal And the Tate diagonal is the subject of the classical thsegal conjecture. So one might wonder what the thsegal conjecture looks like or has to say about this cyclotomic Frobenius. But I'll also mention that this phi, for example, appeared earlier in, e.g., the thesis of Luno-Nielsen, who really highlighted the importance of this map and the study of the thsegal conjecture for this map. So the THH-thsegal conjecture is the question of to what extent is this phi map in equivalence? Since we knew that the Tate diagonal is an equivalence for any bounded below x, one might hope that something made out of it is also an equivalence for a large variety of rings R. And essentially, for the rest of the talk, I just want to walk through some examples of what this phi map looks like and how close it is to being an equivalence. So the most basic example would be if we plugged in the sphere itself. So if one plugs in the sphere, we can just calculate the THH of the sphere. Well, that's given by some funny formula, the sphere tensored the sphere over the sphere tensor with the sphere op. The sphere is commutative, so I don't really need to write that op. And this is some convoluted way of just writing the sphere back again. So THH of the sphere is the sphere, and the map, the cyclotomic Frobenius map, is not a mystery. It's going to be some map from THH of S to THH of S TCP. So that, in other words, is a map from the sphere to the sphere TCP. And this is the Tate diagonal for the sphere. In particular, by the classical thsegal conjecture, this is a p-adic equivalence. And by Lin's theorem at the prime 2, this is the original start of the whole business. But let's do some other examples where this cyclotomic Frobenius is really of a genuinely different character than just the Tate diagonal we already constructed. So the next example we could consider is when we plug in the ring mu. So first one has to compute THH mu, and this is given by mu tensor over mu tensor mu. Again, I don't need to write the op because mu is E infinity. By the Thom isomorphism, I know that mu tensor mu is the same as mu tensor sigma infinity plus bu. So after applying that Thom isomorphism, we can recognize this entire expression as just mu tensored with sigma infinity plus the point crossover bu with point, or in other words, mu tensor sigma infinity plus of su. So the THH of mu is the mu homology of su. And then one can analyze this cyclotomic Frobenius, and it's an amazing result of Luno-Nielsen and Rognus, that just as in the case of THH of the sphere, THH of mu mapping to THH of mu TCP, this is a p-adic equivalence, or a mod p equivalence. And this is not simply a Tate diagonal. This is some genuinely new map, which is also a p-adic equivalence, perhaps for some kind of similar reason that the Tate diagonal is a p-adic equivalence, but not clearly for the same reason. Now let me throw down another example. We talked about the sphere, we talked about mu. There's a natural filtration running between the two. So we could consider R equals xn, which are these spectra introduced by Ravenel that are the Thom spectra of the map from loops SUN to loops U, which is BU. And then Angelini Knoll and J.D. Quigley, they studied the cyclotomic Frobenius for this xn, and they proved that this Frobenius map is again a p-adic equivalence. it seems from the examples so far very plausible that the thsegal conjecture might have an affirmative answer in this THH variant as well, that this map might always be an equivalence. But there's something special about these examples that we've run so far, the sphere mu xn, and maybe one way of saying what's special is that they all have infinite height. They're all living over mu. They see all the VIs from chromatic homotopy theory. And one sees some intriguingly different phenomena happen when plugging in a ring that is of finite height. So as an example, we could think about R being Fp. This is perhaps the simplest example of a ring that has finite height. And so pi star of the THH of Fp, that is just Fp adjoin x, where the degree of x is 2. I say that's just that, but that's a very deep theorem, which is responsible for a whole lot of math. This is Hocksted's theorem, this calculation that the THH of Fp is a polynomial ring. And we can look at the map into the THH of Fp TCP. And this thing turns out to just be Fp adjoin x plus minus, and this is the map that inverts x. Okay, so now we have a map from a polynomial ring with x in degree 2 to the ring with x inverted. Is that an isomorphism? No, these rings are not the same. So the THH-thsegal conjecture has failed. However, this is an iso in a range. This is an isomorphism, say for star greater than or equal to -1. So we begin to see an example of phenomena happening only for sufficiently large degrees. So let's do another example. We could consider R equal to Fp adjoin T with the degree of T equal to 0. So this, I just mean an ordinary ring, again, a classical ring. This is the polynomial ring in one generator, and viewing it as an Eilenberg-MacLane spectrum. So we can calculate the THH of this ring actually fairly easily. Why is that? That's because the THH of R is just going to be the THH of Fp tensor over sigma infinity plus of the natural numbers. Fp adjoin T is just Fp tensor sigma infinity plus of the natural numbers. And that is this tensor product, because THH turns out satisfies some sort of Kunith formula. It's a symmetric monoidal construction. And it's relatively straightforward to compute THH of sigma infinity plus of the natural numbers from the definition. So anyway, when one computes all this, we can then study this cyclotomic Frobenius, and that's going to be some map from pi star THH of Fp adjoin T to pi star of THH Fp adjoin T TCP. And this is just Fp adjoin xt, but tensored little exterior algebra on sigma t. So here the degree of x is 2. That's that Boxstead generator again. T we said was in degree 0, and sigma t will be in degree 1. And then this ring is isomorphic to Fp adjoin x plus minus t tensor over Fp with this little exterior algebra on sigma t. And this map, again, is just inverting x. Okay, because we have now introduced an exterior generator, the range in which this isomorphism has changed, because that exterior generator is in positive degree. So this is, again, an isomorphism in a range, but now the range is for star greater than or equal to 0 instead of for star greater than or equal to -1. So this exterior generator slightly weakens the range in which the thsegal conjecture is true. So just to sort of repeat myself again, but in slightly more generality, we could also consider something like a polynomial ring in many generators. So some kind of d-dimensional ring. And again, I just want to be thinking about this as a classical ring, so all the degrees of the Ti are 0. And then again, by Acuna's formula, it's straightforward to compute what this map is doing. And what it's doing is sending the polynomial ring adjoin the Boxstead generator X, tensor a little exterior algebra, now on generators sigma T1, sigma T2, up to sigma TD, and it's mapping that to the same expression where the only difference is that we now invert this Boxstead generator X. So I'm belaboring this explicit computation for a polynomial ring because in some sense, I think it's the only computation that one needs to really understand what's happening with the Quillen-Lichtenbaum conjecture and the ranges involved in it. And so let me just remark that this is an isomorphism now only for star greater than or equal to d minus 1. So why d minus 1? It's because now we have this exterior generator and that has some top exterior power that we have to worry about, which is the product of all these sigma ti's. And that's still a finite number. So we do get a thsegal conjecture in a range, but the range is getting worse. So let's do something a little bit more sophisticated now than a polynomial ring over Fp. So we could consider, for example, R being Vp adjoin T, with the degree of T being 0 again. So now if you tried to directly compute the THH of Zp adjoin T, it would actually be a little bit messier and not as nice, because the THH of Zp doesn't have as clean a formula as the THH of Fp. But there's a nice observation here, which is that this R comes equipped with a filtration. So if one takes the p-adic filtration of R, this has associated graded something a little bit more simple. So this has associated graded Fp adjoin V0T, just filtering the p-adics by the powers of P. And this induces a filtration on THH of Zp adjoin T with associated graded THH of this polynomial ring over a finite field. Now we know that the thsegal conjecture is true for this finite field. We know that if we map this to its Tate construction, at least in some range, we'll get an equivalence. Right, so the precise range when we had two variables was that this would be a pi star iso for star greater than or equal to 1. And since we know that, we can just directly conclude that if we do the same construction with Zp adjoin T, that will be also a pi star iso, at least if we p complete both sides. And that's just because to check whether a map is an isomorphism, if there's a filtration on the map, you can just check that the associated graded is an isomorphism. And so without ever actually computing anything about the THH of Zp, one can deduce some kind of thsegal conjecture just by using the fact that it has this filtration in terms of polynomial rings. So let me introduce a deeper result, which is sort of a very key ingredient in the computations of Asuni and Rognus. So remember that they were looking at a prime greater than or equal to 5 and studying this atom summand L. And one of the key first things they do in that paper is compute the THH of LP completed mod PV1 to THH of LP completed mod PV1 TCP. And they observe that this is a pi star iso, where star greater than or equal to 2p minus 1. So there's something interesting going on here because this is higher chromatic. We're not just claiming now that a map is an equivalence after p completion, the same way we were with all the earlier versions of the thsegal conjecture. Now we're claiming that a Frobenius is an equivalence after modding out by both p and v1. And the range is this interesting number. And one might wonder, okay, so everything we've done so far has been about p completions. How is v1, how is the higher chromatic v1 entering this story? So let me give a sort of a historical proof sketch of how you might prove this version of the thsegal conjecture. And this is based on some cool ideas of Dylan Wilson that we explored in a paper together. So the idea here is that we can again filter this p completed L spectrum. Even though we don't really understand the L spectrum very well, at a level where its THH is supercomputable, though the THH was computed by Engelweit, Lawson, and Hill, the answer is complicated. In any case, we can just filter L by its Adams filtration. And that's some higher chromatic analog of filtering ZP by its p-adic filtration. So the associated graded here is just FP adjoin V0 and V1, where the degree of V0 is 0, and the degree of V1 now is 2. So we're in pretty good shape now because the associated graded is a polynomial ring. The only wrinkle is that now one of the generators is in positive degrees, whereas previously all the polynomial generators were in degree 0. Okay, but nonetheless, we could attempt to study this cyclotomic Frobenius on the THH of L by a spectral sequence, which would have associated graded the cyclotomic Frobenius on the THH of this polynomial ring. And the formulas are just as easy to compute as before and look very analogous to what came before. So here we're going to see a polynomial ring with a Boxstead generator attached and a little exterior algebra on sigma v0 and sigma v1. And here we're just going to see that same expression as always, but with the Boxstead generator inverted. And now I just want to note the degrees that everything is in. So the degree of v0 is 0, the degree of x is 2, the degree of v1 is 2p minus 2. Sorry, this should be a 2p minus 2 here. And the degree of sigma v0 is 1, and the degree of sigma v1 is 2p minus 1. In any case, this is a very explicit formula for the associated graded of this spectral sequence converging to the Tate diagonal, or to the cyclotomic Frobenius. And this is not an isomorphism in any range. Unlike in the previous examples, there's no range in which this is an isomorphism, and that's just because we have this element v1 in positive degree, which was previously in all other examples maybe something in degree 0. And that gives rise to classes like x to the minus a, v1 to the b, that appear on the right-hand side in every even degree. There are classes involving negative powers of x in every even degree now, and so this map is not an isomorphism in any range. However, this does become an iso exactly after we leave the range of these exterior generators, after we mod out by V1. So if you kill V1, then all your polynomial generators move back to being in degree 0. You've killed the one in positive degrees, and this will be an isomorphism for exactly the same reason as before, except for a little bit of the fuzz at the beginning coming from this finite exterior algebra. So if we go back up here, that says that as long as we additionally mod out by V1, this is going to be a pi star isomorphism in a large range. Okay, so that's sort of how I see the thsegal conjecture coming about, and how I like to think about its higher chromatic versions. It all just comes down to this one calculation of a polynomial ring, and understanding what you have to mod out by in order to make that calculation become an equivalence. Let me end in the last few minutes by talking about the relationship with that Quillen-Lichtenbaum conjecture that we started with. Okay, so remember the theorem of Asuni and Rognus was that the K theory of little l, P completed, say, mod P and V1, mapping to the K theory of little l, P completed, mod P V1, join V2 inverse, that was supposed to be a pi star iso for star large. And let's just sketch the proof. Again, this is going to be an ahistorical version of the proof. So the first thing to remark is that we can reduce to the same statement for TC. And I'll remind you of what TC is in a moment. But replacing K theory with TC is something we can do by the Dundas-Goodwillie-McCarthy theorem. The difference between K theory and TC will be controlled by a classical ring, and we'll take as given the Quillen-Lichtenbaum conjecture for a classical ring, say, like ZP, as it was computed by Hesselholt and Madsen. And now what we need to show, another way of phrasing this condition that you're a pi star iso, is that TC of LP be mod out by P, V1, and V2, that this is bounded above. That's the key thing to show. We want to show that that has trivial homotopy groups above some range. So I need to remind you quickly what TC is. It's got a formula that is given by Nicolaus and Schulze in recent work. So in order to compute TC of something, we need to compute the fiber of a map from THH of L, in this case, HS1 to THH of L, TS1, again here using this circle action, and the map you want to compute is phi S1 minus can. So phi was some map before I put in the HS1s and the TS1s, but when I take the S1 fixed points of phi, I get a map of this nature, and the canonical map that I subtract from it is the map that always exists for any S1 spectrum between the homotopy fixed points and the Tate fixed points. Okay, so we want to understand how this formula behaves after we tensor with P S mod P V1 V2, and we'd like to show that the result is bounded above. So the first thing to note is that tensoring with S mod P V1 V2 is a reasonable operation from the point of view of this formula because it commutes with all limits. And that's because this is just a finite complex we're tensoring with. Another thing to note, which is an ingredient I haven't discussed at all and won't discuss with at all, it's the other major ingredient in this story, is that after reducing mod p v1 v2, this canonical map is 0 on pi star for star sufficiently large. That's a slightly different story, but also an important one. That the canonical map essentially goes away in large degrees after modding out by p v1 and v2. So since the canonical map can be just treated as though it were 0, we essentially need to compute the fiber of phi hs1. But we checked something about pi star phi. We've checked that pi star phi is an isomorphism mod even p in v1 without even involving v2, and that's true for star greater than or equal to 2p minus 1. And if phi itself is an isomorphism in some range, the fiber of phi will be bounded above, and taking homotopy limits will take bounded above things to bounded above things. Or in other words, pi star phi hs1 is also an equivalence in the same range. And so that's sort of my ahistorical proof that the TC of L mod p v1 and v2 is bounded above. One can see that in some sense, the key calculation forcing us to have this kind of bound is just the calculation of the cyclotomic Frobenius on a polynomial ring over a finite field. So maybe I'll just mention in the last 3 minutes the sort of generalization of this that Dylan and I recently proved. So we checked that for each n, maybe let's let fn plus 1 denote a type n plus 2 complex. Let's see, did I get the, yeah, so L, yeah, type n plus 2 complex. Then for an appropriate ring structure on BPN, one has that the pi star of this TC of BPN tensored with this finite complex is finite. In particular, bounded above. Even more than that, actually finite. So finitely many homotopy groups and finite groups in each degree. The key point for some kind of Quillen-Lichtenbaum statement is this bounded above property. And then just to convince you of the supremacy of the thsegal conjecture in this story, the importance of the thsegal conjecture in this story, let me advertise the following result of Akil Matthew. Suppose A is any BPN algebra such that this Frobenius map tensored with this finite complex is truncated. Truncated being another word for its fiber is bounded above. Then fn plus 1 tensor tr of A is also truncated, which will imply, for example, that fn plus 1 tensor tc of A is truncated. So as long as one has this theorem of myself and Dylan, when you're going on to study algebras over VPN, the thsegal conjecture is the only thing that matters from the point of view of these Quillen-Lichtenbaum statements. So that's a nice result of Akil, and I'll end there.